session. As usual, if you have any kind of question, write Q in the chat for question and F for follow-up. So as last question of today, we have Daniel Harlow's second lecture. I guess there's no need to present him again, so I leave the stage to him. So please.
All right, thanks a lot. So yeah, so today, so last time was kind of an overview of black holes and quantum gravity. Today we're going to get a bit more into the details. So we're going to talk about the classical physics of black holes, a bit about quantum fields on the black hole background, and we'll try to at least sort of sketch the argument that leads to the Bekenstein-Hawking entropy formula and also the black hole information problem. So hopefully you're familiar with the Schwarzschild metric. Looks like this. So this is not the way people usually write it, but it's the way I like to write it. dt squared plus r over r minus rs dr squared plus r squared d omega squared, where so this is the unique spherically symmetric solution of Einstein's equations with no energy momentum present in the system, so just pure gravity. If you break spherical symmetry, there are other solutions. For example, you can have gravitational waves propagating through space and so on. But with spherical symmetry, this is all you have. This r, t, and omega, so this is the round metric on S2. So I'll just, for simplicity, work in 3+1 dimensions in these lectures. So a large R, okay, which means R is large compared to RS, then this metric just goes over to the flat space metric in polar coordinates, plus dr squared plus r squared d omega squared, okay, which is the metric of flat space in polar coordinates, well, flat space time in polar coordinates. So if you study the motions of test particles, in this geometry, you learn that this parameter rs really should be interpreted as 2 times g times m, where this is the mass. So if you have particles zipping around in this geometry at some radius which is large compared to this rs, then they just behave as if they were orbiting a point mass of mass m. So this geometry just reduces to the Newtonian geometry of particles orbiting the sun and so on, when r is large compared to this scale rs. And I guess if you're one of these people who likes putting in pointless constants, then I can write divided by c squared here. So in fact, this radius is called the Schwarzschild radius, which I'll do my best to spell. Schwarzschild radius. Now, there are 2 places where this metric looks singular. So there are 2 apparently singular radii. Okay, so one of them is clearly r equals 0, right? If I put in r equals 0 here, then this term is infinity and this term is 0, and that doesn't look like a very good metric. And in fact, this is called the singularity. So this is indeed this metric is indeed singular at r equals 0, and in particular, near here, tidal forces go to infinity. Okay, so if you find yourself in the vicinity of the singularity as you get closer and closer to it, the forces on you are stronger and stronger, and eventually you're just torn apart no matter how strong you are. So So the singularity really is singular. It's not only apparently singular, it's actually singular. On the other hand, right, so there's also, so, you know, from the point of view of this metric, you know, there's also a singularity when r equals rs, right, when r equals the Schwarzschild radius, okay? So then, okay, before it was this term that was infinity and this term that was 0. Now it's this term that's infinity and this term that's 0. So it doesn't seem that different a priori, just looking at this metric. This is called the horizon. But actually, near here, tidal forces are small. Okay, that's not obvious looking at the metric. I mean, the only difference between these two terms is the sign, and it's not so clear why changing the relative sign should make the tidal forces infinity in one case and small in the other case, but it does. So that means that nothing particularly interesting happens when you're at the horizon, at least according to this geometry. If you're sitting there in this geometry, you know, there are some small tidal forces which are basically controlled by the ratio of your size to the Schwarzschild radius, this parameter rs. But as long as that's small, then you don't really feel any substantial tidal forces. You just coast on through. On the other hand, although nothing locally is special about the horizon, there is something global that's special about the horizon, because when r is less than rs, right, the relative sign flips. And so what that means is that the coordinate r becomes time-like. Right. So previously, you know, whether you're time-like or space-like is controlled by the signs here, right? Like here, this minus sign is what tells you that this is time and this is space, right? But that sign flips here when r is less than rs. And so what that means is that once you get into this region, you're kind of in big trouble, because once you're in this region, then r becomes like time and t becomes like space. And in particular, since r is now like time, you can't go backwards in it. So if you cross from r greater than rs to r less than rs, then your r is decreasing. And just as right now in this room, my t is increasing and there's nothing I can do about it as much as I would like to. Similarly, once you're behind the horizon, your r is just going to keep decreasing no matter what you want, no matter what you try. You will just inexorably be pulled towards smaller and smaller r. And so eventually you die at r equals 0. Okay. So that's kind of the basic physics of the Schwarzschild geometry at the most broad level. We'll say more, but let me first stop and ask if there are questions about what I said so far. I hope the symbols are intelligible to people. I guess this is one of the points where I'm not totally sure about the background of all the students. I will say as an editorial comment that if they're not familiar and you want to think about black holes, then it's in your interest to make them familiar. Although I'm afraid I'm not going to do it here. Okay. Now to better understand, so let's think more about the global structure of this. Okay. So the metric written this way is called the Schwarzschild metric, but moreover, it's in a specific set of coordinates. So these coordinates r, t, and omega are called Schwarzschild coordinates. And they have several convenient features. One is they make the spherical symmetry manifest, and another is that they have this nice feature that at large R, you kind of match nicely onto this flat space metric. So it's useful. These coordinates are useful for thinking about what's going on outside of the black hole for R greater than RS. Well, I don't want to say the black hole yet. Out, just in the region R greater than RS. Okay, that's what these coordinates are useful for. But then they're clearly not so useful at the horizon, right? Because the metric looks singular at the horizon, but actually the space-time is not singular. There's no large tidal forces or anything. And so if we really want to understand the full structure of this space-time, then we shouldn't use these coordinates. They're useful for intuition outside, but we need something better. So the natural thing to introduce are what are called Kruskal coordinates. I think actually sometimes I'm going to butcher this name, but something like that maybe. I can never remember this guy's name. There's if there are any people with the appropriate cultural background, they can tell me how to say this name or how to spell it or whatever. So we want to introduce these Kruskal Sarakas, I don't know, coordinates.
I think it's the Keres, something like that. I mean, Eric had it written in the chat, I think, but I'm not sure of the pronunciation. I mean, my guess is as good as yours.
Yeah, I mean, anything sounds good to me. So anyway, did I get it wrong or right? Oh, I think, I exchanged, yeah, good. I exchanged the K and the R. Okay, that's only a bit flip error. That's not too bad. Okay. In these coordinates, the key point of these ideas, of these coordinates, is that they're coordinates where light moves on 45-degree lines. And so instead of talking about R and T and omega, we instead talk about capital T and capital X and capital omega. And then the relationship between them is like this. So we have T squared minus X squared is equal to RS times RS minus R times e to the R over RS. And then we have T over X equals the hyperbolic tangent of T over RS. Okay. And then the range of these coordinates is that T and X can take any values which are compatible with these two inequalities. Okay. Now, that's essentially because you want R to be positive. Okay, so R being positive gives you this constraint. Okay. Now you can play around with the metric and figure out what it looks like in these coordinates. And what it looks like is that it's 4RS over R times e to the minus R over RS times minus dt squared plus dx squared plus R squared d omega squared. Okay. Now, the details of this don't matter. It's not going to be on the final. But one thing you can see looking at this metric already is that nothing bad happens in this metric at R equals RS. Okay. But something bad does happen in R equals 0. Okay. So by switching to these Kruskal coordinates, we've removed any confusion about whether or not there's something funny going on at the horizon. There clearly isn't anything funny going on at the horizon. Oh, interesting. I'm holding the wrong piece of paper. I want this piece of paper. Very good. that one only had the first page of the lecture. So let's draw a picture. So that'll make it maybe a little more clear what's going on here. So I'm going to draw the plane of t and x. Okay. So if you stare at this inequality, right, like if I put r equals 0, say, in these coordinates, right, then that sets this thing equal to rs squared. So that kind of the singularity lives at one of the upper bounds of this. And in fact, it's like some hyperboloid. So let's see, I'm very bad at drawing this, but I'll do my best. So there's some 45-degree line like that, and some, I should extend it down, and some 45-degree line like that. I guess I should draw negative axes too. And then this line where t squared minus x squared is equal to rs squared is some hyperboloid like that. And then the lower inequality is some hyperboloid like this. It's very hard for me to do this on the fly, but I'm doing my best. So that should be symmetric, even though it doesn't look like it because of my personal limitations. So then this upper hyperboloid has r equals 0. And if you look at this formula, actually the lower one also does. Okay. And then, how shall I say? Oh, I think I made a mistake here. I should have only written one of these inequalities. I should erase. Yeah, I think I was thinking to myself as I wrote it that it looked funny. I just shouldn't write this inequality at all, except is my eraser not going to work? Oh, I think I have to try that. Okay, well, okay, I'll just cross it out. My eraser is not cooperating. All right, now I just want to write this inequality because there's a square here. So this inequality implies that I have to be both below this hyperboloid and above this hyperboloid. So this geometry has 4 regions. It has this wedge on the right here. It has this wedge on the left here. It has this future wedge here, and it has this this pass wedge down here that my bad drawing kind of compressed a little bit. And so in this geometry, there is a singularity both down here in the past and up here in the future. So remember, t is like time going up, right? You see t always has the minus sign here. X is like space going left and right, okay? So this yellow line here is a future singularity. It's the place where if you go there, you die. This yellow line down here is a past singularity. It's also a place where if you go, if you die, you die. Now, the amazing thing is that if you look at this equation, if you take x to be large, and either large and positive or large and negative, if you look at this formula, r becomes large, okay? And what that means is that this geometry actually has 2 regions that look like flat space, okay? There's a region over here that looks asymptotically flat. And then there's another region over here that also does. And so this is actually 2 universes. The word is, it's sometimes said, although I think it's a little bit silly. 2 asymptotic regions, maybe is better. I'll say asymptotic regions, which are connected by a wormhole. Okay, but remember I told you that in Kruskal or Kruskal-Sakaris coordinates, light moves on 45-degree lines. And so you see what this picture tells you is that means that light can never get from one asymptotic universe to the other. Because if I'm down here in this asymptotic universe, even if I send a signal very early, it's always going to end up in this singularity here, and it's never going to make it over to the other side, and vice versa. So this is a non-traversable wormhole. And that's the global structure of the Schwarzschild geometry. You have these two asymptotically flat regions. There's a wormhole in between. In the interior region, there's a singularity in both the past and the future. And anyone who tries to go through the wormhole ends up dying in the singularity. Any questions about this? Yeah, go ahead.
So here, just a wormhole is simply just the fact that these regions are connected when you have these coordinates, right? Do you have any other physical structure to this wormhole apart from simply the mathematical structure of the space right here?
Well, I guess maybe the key thing is that there are space-like curves that connect one asymptotic region to the other. So the two regions are physically connected. And in particular, although I can't go through, I can jump in from this side and you can jump in from that side and we can meet in the middle. And so that's in some sense physical, right? You know, neither of us can then tell our friends about it outside. But yeah, people often make, you know, analogies to Romeo and Juliet, right? Because, you know, they're separated in asymptotic universes, but they can meet each other and enjoy life briefly if they're willing to die for it.
So there's another question by Vincenzo.
Yeah.
Yes, so almost the same. I was not able to understand why you cannot go from one zone to another through the wormhole.
Yeah, so well, that unfortunately, this is my picture makes this less clear than it should be because I'm not good at drawing pictures. But the key point is that this yellow dashed line here is supposed to be a 45-degree line. I don't know. Do people do degrees in Europe? I can call it a pi over 4 line if that helps. It's half of a right angle. So light moves on 45-degree lines in this picture. So that was kind of, it's not totally obvious, but if this thing here in T and X is just the flat metric, and it turns out that null geodesics don't care about the factor here. So the light rays here go on 45 degrees, and you can't go faster than light is the issue. Okay. So if you could go faster than light, then you could have a slope that was, you know, more like that, and you can make it over. But anyone who can't go faster than light, which is anyone since we're doing general relativity, can never get from one side to the other. Does that help?
Okay, thank you.
Yeah. Anyone else?
So there's a question by Pavan.
Yeah, Pavan.
So which of the spaces are greater than RS?
Oh, you mean in this picture?
Yeah.
Yeah. Let me label that. So so in the blue region, in both of the blue regions, we have R greater than RS. And in the green region, we have R less than RS, and also in the red region, we have R less than RS.
Right. So in real life, R greater than RS, any two people in R greater than RS can meet, right, outside the black hole.
Yeah. So I mean, so like, well, this is not quite yet a black hole. We're going to discuss black holes in a minute. This is a wormhole.
Right.
Yeah, but anyone living out here, just, you know, from the point of view of someone living out here, there's just some object here, you know, with some size which is of order RS, and if you're far away from that, you don't really care about it too much, unless you're a physicist or a philosopher, I guess. Okay. So yeah, now let me address this question of black hole or wormhole. So contrary to what you may have heard, the Schwarzschild geometry does not actually describe a black hole. This is a vacuum solution of Einstein's equation describing a wormhole connecting two asymptotic universes. Okay, whereas a black hole, I would say, although this is a matter of definition, but I think this is the correct definition, is it's an object that's created by gravitational collapse in a universe with one asymptotic boundary. It's not something that's connected to another universe. So certainly that's what an astrophysicist means when they say black hole. You know, they mean something that came from stellar collapse or from the formation of a galaxy. And so to describe a black hole, though, of course, I didn't tell you about the Schwarzschild geometry for no reason. So for a real physical black hole, the Schwarzschild geometry is a good description of what's going on outside of the matter that you collapse to make the black hole. But then in the region where the matter is, now the geometry is going to be different, right? Because now there's matter and it sources the geometry in some way. And in particular, it's going to have to get rid of this other universe through the wormhole because that's not really there, like for an astrophysical black hole. So to introduce that, let me first draw. So somehow we have to collapse. So we somehow have to make a collapsing matter shell. So I'm just going to do that by drawing a picture. But before I do that, I want to draw a sort of idealized version of the picture I just drew. So this is called the Kruskal diagram. Maybe you see it's a bit busy. You have to kind of deal with these lines going off to infinity. So there's something called Penrose diagram, which is basically the same picture, except it moves the points at infinity into finite distance, just to make sure that you really know everything that's going on for sort of arbitrarily long times and large distances. So so the Penrose diagram for this, for the Schwarzschild geometry now without matter, looks like this. So hopefully I can do a little better drawing this one. Well, I didn't start out good, but so it looks like this. So the basic idea is the same. We have the four regions. This one up here is the green region. This one down here is the red region. And then we have the two blue regions on the left and right. And then there are names that people give to the various parts of infinity. I'm not very good at writing them, but like this one is called scry plus. This one is called scry minus. This one is another scry minus. This one is another scry plus. This is I plus. This is I plus. This is I minus, this is I minus, this is I0, and this is I0. So the idea is that, and then this is these are the singularities. So maybe I'll write the singularities in red. So these are the places where if you go there, you die. And I can try to adopt the same color scheme I had before. So Penrose wouldn't put the colors there because that's too, he wants to be very austere, but just to help you compare the pictures, I'll add the colors. And you can see the same thing. So again, light moves on 45-degree lines, right? So someone over here can never send a 45-degree line over there and vice versa. But now we have the advantage that we brought in infinity to finite distance. So there's the whole space-time right there with no points missing or left to your imagination. And so the names are this scry plus is future null infinity. This scry minus is past null infinity. I0 is spatial infinity. I plus is future time-like infinity. And I minus is past time-like infinity. But don't worry too much about the names. I'm just telling you what they are in case you see them sometime in the future. Okay, so that's the Penrose diagram for the Schwarzschild geometry. Now let's draw the Penrose diagram for gravitational collapse. And so actually I'm going to draw two different diagrams. So I'll first draw the diagram where we collapse some massive matter. So like a star. So maybe here's a star. It undergoes a supernova. Its core collapses. So there's some region where all that matter is. And then it collapses to a singularity. There's a horizon. And so it looks, okay, I'll expand my matter here some. Okay, like that. Okay. I'm really butchering this. Okay. So this is like an astrophysical black hole. So the region outside of the red is just a piece of this Schwarzschild Penrose diagram here. So I've got part of the green interior here. I've got part of the blue exterior over here. But then once we encounter the matter, now the geometry changes because there's no, well, it's Einstein, the equation has to be obeyed. And the geometry just caps off here at some kind of origin of polar coordinates. And so there's only one asymptotic region in Neptune. Now, in fact, we can draw an even nicer picture if instead of making the black hole out of massive matter, like what happens in a real black hole, we instead make it just out of a shell of massless particles, which moves on a 45-degree line. Come on, there we go. So then we just have some picture like this. Oh, no, come on. Let me extend this a little bit further. That, and then there's some horizon like this. Okay, and then so everywhere above the shell, we have like a piece of this Penrose diagram of the full Schwarzschild geometry. Then we've got the shell, and then below it, we can just have the shell all come in at one time, and then below that we just have flat space. So down here we have flat space, and up here we have Schwarzschild. So that's what an astrophysical black hole looks like. So the main differences are with the Schwarzschild, it only has this future component of the horizon. It doesn't have this past component. There's only a singularity in the future, not a singularity in the past, right? In the past, there's just the star or whatever, and then just flat space before that. And then you don't have this asymptotic region on the other side. Okay. And so this is what deserves the name of black hole. This is what a black hole actually looks like. It's some object, you collapse. After you've collapsed, you've got some piece of Schwarzschild outside. Okay. Any questions about astrophysical black holes?
So there's a question by Siddhartha, please.
Yeah.
Just a brief clarification. So the horizon doesn't exist before the collapsing shell.
It does actually. Yeah, it does. This region here is this dashed line here is part of the horizon.
No, but it only forms once we have the collapse.
No, it's actually not true. So this comes down to what the definition of the horizon is. So the definition of the horizon is that it's the boundary of the set of points which can send signals to null infinity, let's say. Okay. So if you're living down here, okay, say you're living down here. Okay. You're just living in flat space as far as you know. Okay. But your doom is sealed. You don't even know that this shell is coming, right? It's over here and you're somewhere in your future. You know, it's going to hit you later. But even before it hits you, you're already in the part of the geometry where you can't send a signal that gets out. Whatever signal you send is going to end up in the singularity. And so this boundary between people who can communicate to infinity and people who can't is the definition of the horizon.
Okay, thanks. Yeah.
It looks like there's a long question somebody just asked. Why don't you ask your question, Shashank?
Hello. Sorry,
Yeah, hi.
My audio, I don't know if you're audible to me. My connection is not quite good.
Oh, I see.
Yeah, if I'm audible, can I go ahead with the question?
Yeah.
Yeah, I'm asking the Schwarzschild coordinates. When we set up the solution, we choose R to be space-like from the beginning. And for a faraway observer, dr measures just the distance as measured by the faraway observer. When you suddenly make R as a time like you have from the beginning when you set up the solution chosen R to be space-like. So how do you reconcile the fact that now that R has suddenly become time like, what does dr measure for the faraway observer?
Yeah, so the way you should think about R is what it's really doing is it's telling you the size of this two sphere. Okay, that's what it's always doing.
Right. So you mean that the two sphere is so the two sphere inside the horizon is somehow increasing in size at some one position of the space-like coordinate. The two sphere is increasing in size.
Yeah,
Inside
inside the two sphere is decreasing in size,
Yeah,
because
sorry.
it's going to end up at r equals 0, right? Yeah, and so the idea is once you're inside, once you're at r less than rs, you can't stop the two sphere radius from decreasing. And when it gets to 0, you die.
Right. And just one more thing in the Kruskal diagram,
Yeah.
in the part where you have drawn it from for the, I mean, from the purpose of astrophysics or the purpose of astrophysics.
Yeah.
How did you delete this second part of the, I mean, this part in the third quadrant? I mean, you're only having the parts from the fourth and the first.
Well, I have to solve the Einstein equation. So once there's matter present, I can't just write down the geometry I wrote down before, because that was a solution of the Einstein equation with no matter.
Okay.
So I didn't tell you in detail what the solution is. I just drew the picture so that to try and hope that it would be plausible. Here I can even tell you the solution, though. It's just you take the piece of Schwarzschild above this null surface, and then you take empty flat space, which I also told you the metric of. It's this one, right? Below the shell. And then you glue them in some way which is determined by how much energy there is in the shell. And that's how you construct this solution. So this is a pretty easy solution to construct. This is, I drew the other one though, because this is not how black holes actually form, right? In the real world, right?
Yeah.
Black holes form in some messy way that looks more like this, but for theoretical considerations, it's better to think about it this way.
That makes sense. Thank you.
Yeah. Okay. So that's kind of all I was going to say about classical black holes. Oh, is there another question from Pavan? It's F, but maybe F means Q.
No, there's a follow-up.
Follow-up.
Oh, follow-up. Okay, go ahead.
Right, to what Siddharth was asking. So this green guy, does he observe that his R and T coordinates have exchanged signs?
No. I mean, so that's just coordinates, right? So that's the key thing you have to understand about general relativity, is that the coordinates don't matter. So I've chosen the coordinates in some way, right? But for this green guy, it's not true that he necessarily sees the radius of the two sphere decreasing. Okay, he may not, right? If he flies this way, he'll see it increasing for a while. Okay. Once he crosses the shell, then he'll definitely see it decreasing. But the important thing about him is that, so that's just a local criterion that happens to be true in the Schwarzschild geometry, but the real definition of the horizon is whether or not you can communicate with infinity. And he can't, so he's behind the horizon. Okay, so that's kind of it for classical black holes. I would say that classically, black hole physics is fairly well understood. There are general theorems that characterize the behavior of Einstein's equations. And in many cases, you can solve them analytically or numerically and compare to data. So for example, like LIGO, which hopefully you heard of, detected gravitational waves from the mergers of black hole binaries. And they can compare the wave profile that they get to numerical solutions of the Einstein equation for two merging black holes, which is a very sort of strong test of general relativity, and it seems to work. Okay, so classically, yeah, you have to wrap your head around these coordinates and the Penrose diagrams and whatever. Okay, but if you think about it for a couple of weeks, you're going to understand it. On the other hand, as we discussed last time, once you introduce quantum mechanics into the story, then things become a lot more puzzling. And we now don't have an understanding that approaches the level that we have in the classical situation. And so that's a long road, and we'll talk about some of it in these lectures, but today we're going to start with the sort of minimal amount of quantum mechanics that we can imagine turning on, which is just quantum field theory in a black hole background. And so what that means is that the matter is quantum, but the metric is classical. So that may sound like an inconsistent thing to do. How can some of the degrees of freedom be quantum and some of them be classical? But there is actually a limit where it makes sense. And so this is a limit where we take g Newton to 0, but we fix g times m. Okay. So this is Schwarzschild radius. So we keep the radius of curvature fixed, and we turn off all of the gravitational interactions. And so in that limit, the graviton just becomes a free field that doesn't interact with any of the other fields, and we can just choose to ignore it. And so that becomes quantum field theory in a fixed background. And then towards the end of the lecture, we'll try to back off a bit of this limit, but this is where we'll start. Now, to talk about quantum field theory in the black hole background, we have to first talk a little bit about quantum field theory in general. Okay, since maybe not everyone here is a quantum field theory expert. Maybe you are, I don't know. But I'll assume you're not. So the basic idea of QFT is that there are independent degrees of freedom at each point in space. So if you try to express that mathematically, you might say that the Hilbert space H is a tensor product over all the points in space of some Hilbert space Hx, where this Hilbert space is the degrees of freedom at x. Okay, and so I emphasize that when I put a little arrow on x, I mean it's a point in space at a fixed time. Okay, so if I'm talking about the space-time point, I won't put the arrow, right? So so for example, we could consider a scalar field theory. With a single field, phi of x. And then we could have a basis of the Hilbert space, F, which are labeled by functions F from R3 to R. Okay, and then the way this basis works is that if I act with the field on F, then I just get F of x times F. And so there's a single, real degree of freedom at each point in space. I can adjust them all independently, and so the values at the list of all the values at each point in space is this function f, right? And then I have a complete, I have a complete basis for any so for any two functions f that are not the same, these states are orthogonal. That's a bit heuristic. If you're a sort of mathematically minded field theorist, you'll find what I just said offensive, but it basically gets you the right idea, without worrying about subtleties related to renormalization. So then, so that's the Hilbert space, right? To do quantum mechanics, I have to tell you the Hilbert space and I have to tell you the Hamiltonian. So I've told you the Hilbert space, now I'll tell you the Hamiltonian. And so the key thing is that so that the Hamiltonian H, we take to be an integral over space of some function h of x, where this is constructed out of the fields and their derivatives at x. Okay. So for example, for a scalar field theory, right, we could consider a free scalar field where we integrate d cubed x of pi of x squared plus nabla phi dot nabla phi of x over all of space, where this pi is the canonical conjugate of phi, right? So we have some commutation relation like and so that's kind of, in some sense, all there is to quantum field theory. You have a Hilbert space constructed out a bunch of degrees of freedom at each point in space that are all independent of each other. And then you've got a Hamiltonian that's a local integral of some Hamiltonian density, which is just a function of the fields and their derivatives at each point in space. Any questions about this? Maybe I'll add, as usual, there will be some, we'll assume that, you know, usually there's some ground state, which I'll call omega. And as usual, we do time evolution by acting with e to the minus iht.
So in a certain sense, we have a sort of bundle of Hilbert space on the Minkowski spacetime. Is correct to imagine this way?
Yeah, I think you can think. Yeah, let me think. Yeah, I'm not quite sure if I would say that, because it's really the tensor product, right? So yeah, I guess you can say this hx by itself is like a bundle, but then I'd have to do this tensor product.
Okay, sure.
Yeah.
Thank you.
Yeah, I guess this hx, we could call it like a vector bundle over space. Yeah, but then we have to take the tensor product of all the vector bundles over the base manifold, if you like. Are there other questions? So I mean, somehow this local structure of the Hamiltonian is kind of the key thing. That's what makes sure that the degrees of freedom in Urbino can't communicate instantaneously with the degrees of freedom here in Cambridge, even though we're doing a pretty good job because the speed of light is pretty fast. Okay. So that's kind of quantum field theory 101. Now we do quantum field theory 102, unless there are more questions. No? Okay, last chance. Okay. So a key feature of QFT is that all finite energy states are very entangled. Okay. So there are various ways to see this. One kind of very simple way is the following. So if you just look at the 2-point function of some scalar field in the vacuum. So you just take the expectation value of the product of two. So that's a correlation function, right? It tells you how correlated the fluctuations of phi of x and phi of y are. Well, when x is close to y, then this is going to scale just like the distance between the two to some power 1/2 delta, where this delta is greater than 0, and it's usually called a scaling dimension. Okay. And what that means is that as you bring the fields closer together in space, their correlation gets bigger and bigger, and in fact is unbounded. It can get as big as you want. And that's true even though this ground state is a pure quantum state, right? And so since the Hilbert space has this tensor product structure, right, this phi of x and this phi of y, they're independent, they're commuting independent operators in the Hilbert space, right? But even though the system is in a pure state, they're very correlated. And that's the definition of entanglement, right? The definition of entanglement is that you have two independent systems in a pure state, but there's correlation between them. And in fact, what we see here is that there exists an infinite amount of entanglement, right? Because we can just bring them closer together, and they just get more and more correlated. There are various ways you can think about why this entanglement has to be there. One that I like is that if you just look at this Hamiltonian, right, you see there's this term which is the gradient of phi dotted with itself. Okay. So if you want the energy to not be too big, then this gradient can't be too big. But if the fields at neighboring points in space were independently fluctuating by a lot, right, then often that gradient would be very big. Because you would just have a big change in phi from one point to the next if they were independently fluctuating. And so to make this gradient squared term small in the Hamiltonian, the fields that are near each other have to be, their fluctuations have to be sort of lined up to a very good approximation, which is what leads to this large correlation that we're looking at here. I suppose you could also try to just have them all be exactly the same, but then that would make this term in the Hamiltonian be unhappy. This term requires them to be fluctuating. So since they're required to be fluctuating, they have to be fluctuating together. Any questions about that?
Yeah, I have a naive question, if I may.
Sure.
What do you mean by infinite amount of entanglement? You mean like that the measure of entanglement, such as entanglement entropy or whatever, tend to infinite?
Right. So that's really what I mean, but I didn't say that. But yes, you can formalize what I said that way. Here I just meant that this correlation can become as big as you want if you bring the points together.
Okay, nice. Thank you.
Yeah.
Just a very brief thing, just to make sure I'm getting with the definition. So before you were saying that an entangled state is supposed to be that you have two pure states with correlation between them.
You have an entangled state is a pure state. So okay, let's write
I was under the impression that pure state was that of the composite system, because then you trace out.
Yeah, that's what I'm talking about.
Okay.
So let's think about a state like this, right? Okay, so the analogy is between this state and the ground state.
Okay.
So the ground state is a pure state of the whole system.
Mm-hmm.
But we can throw out, if we want to look at this correlator, for example, we can throw out all of the pieces of the tensor factorization except for the two at the point, the one at the point X and the one at the point Y, right? But you see, the point is that this being large shows that there's correlation between the two independent parts of the system, right?
Yeah.
Just as there is here, right? In this state, there's correlation between the first and the second qubit.
Yeah.
They're either both 0 or both 1. And so the idea is that this is kind of a model for what's happening here, except here there's a lot more entanglement than there is here, because this is just 2 qubits.
I see, thanks.
Yeah. Siddharth has a question.
Yeah, thanks. Yeah, I understood the argument that you gave about the gradient terms, making it the case that if you can't have too much wild fluctuation between spatial points. So I was just to make sure I get this clear, right? So even though we call this a non-interacting field theory, it's still the case that there are interactions between spatial points, right? Because if I change,
that's correct. Yeah, so so this is terminology, right? So even in a free field theory, this gradient term couples the degrees of freedom at different sites, right? When we say it's non-interacting, what we really mean is that the Hamiltonian is quadratic. So that it can be, so that this theory is actually exactly solvable. I can write down the wave functions of the energy eigenstates, in this basis of F's. Whereas if I added a term like phi to the 4th here, then I wouldn't be able to exactly solve the Hamiltonian, and I would have to do perturbation theory in the coupling of phi to the 4th, or put it on a computer, or do something else.
and those are called interactions because?
Well, because it's interactions between, I'm not sure, I mean, it's kind of a historical thing, I think.
Okay.
It's because people first thought about this in terms of particles. So if you solve this theory, what you find is that it consists of non-interacting particles. So you have excitations of this scalar that are massless particles that are zipping around with some momentum, and there are no interactions between the particles. So the number is conserved, and each one just keeps going in the same direction forever. Whereas if you put a term like phi to the 4 in the action, or in the Hamiltonian, then the particles could scatter off of each other.
Okay, yeah, because ordinarily, like if you think about spin systems, and when people say non-interacting, they would not expect like ground state entanglement, for example, right? Because the Hamiltonian would just tensor product out. Yeah.
No, right. No. It's the sort of particle physics definition of interacting.
Thank you. Yeah. So you can't just tensor product out the Hamiltonian, right? That's just to be super.
No, the Hamiltonian is definitely not a sum of independent terms on the different factors.
Okay.
There are terms that couple the different factors together.
Okay. Thanks. Great.
Yep. Yeah, that's why the vacuum is interesting, even in free field theory. Okay. So far, I haven't made any use of relativity or Lorentz invariance. Okay, what I just discussed here could be the Ising model or something. But in theories that are Lorentz invariant, which are the only kind of theories that we're going to think about in these lectures, we can be a bit more quantitative about the structure of the entanglement, say in the ground state of a quantum field theory. So let's move over here. So let's talk about entanglement in relativistic QFT. So the key thing about, well, there are many nice features of relativistic quantum field theories, but the sort of defining characteristic is that they're invariant under Lorentz boosts. So you can do a boost that mixes T and X, or a boost that mixes T and Y, or a boost that mixes T and Z, and those are all symmetries of the theory. So in particular, I'll just focus on the boost that mixes T and X, which I'll call KX. Okay. So in any quantum field theory that's relativistic, there's some boost operator kx, and in fact, there's a formula for it. We just do the integral over all of space of x t00 plus t, little t, t0x, where t mu nu is the energy momentum tensor. So the energy momentum tensor, there are various ways of defining it. The best way of defining it is that it's the derivative of the action with respect to the metric. But it's also it's the thing you integrate to get the Hamiltonian. So in particular, t00 is equal to this h of x that we talked about earlier, the thing you integrate to get the Hamiltonian. But there's more information in t mu nu than just t00, and so it can also tell you about momentum and angular momentum, things like that, and also it can tell you about the boost generator. Now, in fact, it's convenient to rewrite this as k right plus k left, where k right is I think I didn't want to write the 1/2 there. Okay. K right is the integral from 0 to infinity dx d2y of this x t00 plus t0x, and then k left is the part that you integrate from minus infinity to 0 dx, okay, d2y, the same thing. Okay, so basically what I'm doing is I'm taking space-time. So if you think about how boosts act in space-time, right? Like they act kind of on hyperboloids like this, right? So a Lorentz boost takes this point here, and as you do the Lorentz boost, it moves you along this hyperboloid. If you take a point up in here, it kind of moves you along this hyperboloid. Similarly, down here, it moves you along this hyperboloid, and over here, it moves you along this hyperboloid. So that's how a boost looks. And so this k right implements the boosts on this blue region here, and this k left implements the boosts on this blue region over here. Okay, and so this should look similar to the classical diagram that we were drawing earlier. That's not a coincidence. We're going to use that in a little bit. So hopefully everyone is familiar with Lorentz boosts. The key thing here is that we can split the boost into the part that acts over here and the part that acts over there. Okay. Now, there's a fun little derivation that I went back and forth on, but decided in the end I just didn't have the time to explain it to you in a way that would be comprehensible. So instead, I'll just say that fun with Euclidean path integrals tells you the following amazing thing. It tells you that the ground state of any relativistic quantum field theory has the following expression. I put it e to the minus pi omega I. I'll define these symbols in a sec, but I'll write them first. I right. Okay. Where these are eigenstates of k right. These are eigenstates of k left. Okay. And in fact, this omega I is defined by k right IR equals omega I IR. So in this picture, maybe I'll kind of try to make it red. So I'm describing the state. Oh, that was awful. At t equals 0. Let me try to do this better, like that. So I'm explicitly presenting the ground state of quantum field theory to you as an entangled state, right? I mean, this formula looks pretty similar to this formula over here I had for the qubit, right? We just have some sum over tensor product, where here this is a complete basis. So Kr is some operator that lives only on the right side in this blue exterior region here. Maybe I'll try to draw the picture again just to make it a little less busy. So we have this decomposition of space into the blue left region and the blue right region. This IR is a complete basis of states for the subset of the Hilbert space that lives here. And this I star L is a complete basis of states for the degrees of freedom that live in this left wedge. Okay, so this is called the right Rindler wedge, and this is called the left Rindler wedge. So these are Rindler wedges. And this Kr and Kl are often called the Rindler Hamiltonians. It's a kind of a weird name, but that's what they're called. Okay, and so you see I've taken the state on the right here, right? So as we discussed, the Hilbert space is a tensor product. So what's going on over here is independent from what's going on over here at the level of the Hilbert space. But you see they're entangled like this in the ground state. Okay. Oh, I should also say I have to explain the star, right? So how do I decide which eigenstates to put here and which eigenstates to put there, right? So the relation between the two, so I star L is defined as the action of some anti-unitary operator on IR, where this is an operator called CRT. So it's an anti-unitary operator that's a symmetry of any Lorentz invariant quantum field theory, and it's the operation where you just take the Euclidean path integral and you turn it upside down by rotating by pi. Okay, so this is rotation by pi in Euclidean signature. So it's a famous theorem of relativistic quantum field theory that you always have the symmetry. It's sometimes called CPT, but that's an artifact of 4 dimensions. So CRT is the thing that's true in general. Okay, so the details of this I think don't matter too much. Again, they won't be on the final, so don't sweat it too much. The main point I want to get from you is that there's a formula like this that explicitly demonstrates for you the entanglement between the degrees of freedom in the left half of space and the right half of space for any relativistic quantum field theory. And this formula is really just like this formula with the qubit over here. Okay, any questions so far? Feel free to ask for more explanations about things. I mean, I know I'm going through this fast. I mean, you know, I taught a whole class that was a whole semester this year. So, and this, we're already like in lecture 8 or something. So.
Sorry, just to be super clear, you're just recovering the earlier claim that the ground state is highly entangled with a different argument, right? Or
Well, I'm illustrating it more explicitly because, you know, there I just used this correlation function to argue for it. But here, maybe this looks more like the entanglement that you guys are familiar with. You know, I mean, this is really a formula, like this is a true equation. Well, it's almost a true equation. I have to put a normalizing factor here because the state's not normalized. Now it's a true equation.
And the entanglement across the Rindler wedges demonstrates entanglement between any 2 spatial points. Is that? Well,
yeah. So whenever you talk about entanglement, to be precise about it, you have to split your Hilbert space into 2 pieces. Okay. So I've chosen to split it into the region. So this is the region with x less than 0, and this is the region with x greater than 0. So I've just split space like that. And so I'm demonstrating for you the entanglement between this region where x is less than 0 and this region where x is greater than 0. Maybe I should label that in this, maybe I should label the axes here. This is t and this is x.
And x can be anywhere in space.
Yeah. So space is this yellow line here, and then time is going up.
the omega is still the ground state, or what is the exact meaning of?
Yes, yes. This is the ground state of H. Yeah.
And you still assume a scalar field, or?
No, no. This is true in any relativistic quantum field theory. Interacting, not interacting, doesn't matter. That's this power of the Euclidean path integral. So, unfortunately, I mean, you can kind of see already from the answer that I would have to go through a fair bit to explain this, because, for example, you have to get this anti-unitary operator out of the argument. So you have to think hard about Euclidean path integral. It's a beautiful argument. It's just, it would probably be a lecture by itself to really convey it.
So one can say that potentially all points of Minkowski spacetime in quantum field theory are potentially entangled, because there is this sort of bundle of vector spaces.
Yeah.
The ground state in particular, the entanglement is between the two edges of Rindler.
Yeah, that's right. Yeah, but I can do the split wherever I want, though, right? So I mean, I chose to do it at x equals 0, but I could do it at y equals 0 or at x equals 10, or I could rotate it, right? So I mean, any split you make into two, there's going to be this entanglement.
Mm-hmm. Okay.
So maybe let me make two more comments about this. So the first is that I can take this state, and then I can compute the partial trace. So yeah, maybe let me. I guess I just need the state. So let's say I look at the reduced state on the right. So the definition of that, just to remind you, is we trace over the left system of omega. Okay. So to just say I only care about observations in this right wedge, right? But here, if you look at this formula, right, we can do the partial trace in our heads, right? And what we get is just the square of this normalizing factor times the sum of e to the minus 2 pi omega I, right? Okay. And this is thermal, right? This is just a thermal state, right? We're summing over eigenstates, right? So in particular, we can just write it as minus n squared times e to the minus 2 pi k right. Right? So this is just the thermal state, except we're using kr as the Hamiltonian instead of the actual Hamiltonian. So so I should really say it's thermal with respect to kr. And so that's kind of an amazing thing, right? It says that for any relativistic quantum field theory, no matter how fancy, if you split it into parts and you just look at the reduced space on half of the reduced state on half of it, you just get a thermal state with respect to this, half of the boost operator. So in fact, this leads directly to this famous thing, which is called the Unruh effect, which says that how shall I say this? An accelerating observer in relativistic QFT sees a temperature which is just T equals h bar. So I'll write the h bar in C here for you, just to be nice. H bar A divided by 2 pi C, where this is the acceleration. This is called the Unruh effect. Okay, and this 2 pi is the same as this 2 pi here. You just have to switch to the proper time of the accelerating observer, and that converts this kr into this 1 over a. So this is, it's kind of a surprising thing, right? So this is presumably a true statement about the world. It's very hard to measure because, if you, for everyday accelerations, you can see this temperature is very small because h bar is very small. So in order for this to be large, you need the acceleration to be pretty large. It's fun if you estimate, the typical accelerations of the hydrogen of the electron and the hydrogen atom. That's big enough that this is actually an observable effect on the spectrum of hydrogen. So if you computed the spectrum of hydrogen in the rest frame of the electron, then the Unruh effect would be important in getting the energy levels right.
Sorry, Daniel, there's a question for you by Julie.
Yeah, sure, go ahead.
I was just wondering if this form of, like the exact form that is a thermal state is actually dependent on the fact that you're considering this boost operator, or that you get, or whether you get the thermal state no matter how you split the space into two parts.
Yeah, good. So no, you have to do the split in Cartesian coordinates into half of the plane along a straight line. If you do the split in terms of some curvy region, then this won't be the right formula. But as long as the cut is a flat plane, this line together, yeah, then this formula will be exactly true. Because if you think about it, the boost kind of picks out a line of really a plane of points that are invariant under the boost. And so you have to cut along that plane. Other questions?
So you conclude that we have thermalization because you have something like Boltzmann factors, right?
That's right, yeah.
Right. Yeah. So maybe not trivial for the others, but you might want to say, and that's how you, when you take together the Boltzmann factors, you get the right spectrum, such that from a spectrum you get the temperature.
Right, yeah. So I'm comparing this. So in the standard thermal density matrix is 1/z times e to the minus beta h. Okay. And so the idea is that these two are mathematically the same. This 2 pi is somehow the inverse temperature, and this Kr is playing the role of the Hamiltonian.
Yeah. So my question was relating to the move from a many-body relativistic quantum field theory to to essentially the Fock space, where you have an infinite number of degrees of freedom. And
Yeah.
so in this formula, you have the n squared. So when you let n tend to infinity, then obviously, then so how does that work?
Well, sorry, this is not the number of degrees of freedom. This is just defined to be whatever it needs to be so that the trace is 1. Or yeah, here it's defined to be whatever it needs to be so that this state has norm 1. And so I can preserve that the state has norm 1 in the continuum limit. It's true that things like this, I mean, probably both this there'll be various divergences floating around here that somehow have to be absorbed. And so this n will have some divergence in it in the continuum limit, but it'll be the right divergence so that the state is normalized.
Okay, thanks.
Yeah.
Sorry, can I ask a question? Is there any motivation behind defining this K operator there? Because it seems like angular momentum tensor in field theory. I'm not sure, but it seems like that. But
well, it's half of the boost operator, right? So a boost is like a rotation, except that it's a rotation in time instead of in space. Right. So I mean, this formula looks like, this formula looks a lot like angular momentum, right? Except that
generators of rotation.
T and X instead of mixing X and Y or something, right? So yeah, so the motivation is just, I defined it as half of the boost, but honestly, the real motivation was that I knew that this was going to be the state. So then I knew it was a good thing to define.
And also, we have an analogy between quantum field theory and statistical mechanics. Does it have anything further than this Unruh effect? I think because we can make this.
Yeah, it's not so clear because usually in what you mean there, everything is Euclidean. Usually it's Euclidean field theory is analogous to classical statistical mechanics. But this is really a Lorentzian effect. You know, you have a detector that's accelerating in space-time and it sees this.
Thank you very much.
Yeah.
There's also a question by Siddhartha.
Yeah.
Yeah, just to be clear, so it doesn't actually, you could also use the equivalence principle and to argue, I mean, setting aside black holes, right? Even outside a
Well,
star.
I haven't talked about black holes at all.
Yeah, I'm not talking about them either. Just even outside stars or planets, one would expect an undue temperature, right? Because of the equivalence principle.
No, I think that's not so clear. Yeah.
Why not? Because it's just an acceleration.
Yeah, but I'm not sure what to say. So yeah, okay. Well, sorry. I mean, if you, I'm not sure it's true that you're supposed to see the Unruh effect when you're orbiting a star. That's curved space-time. There may be something like that. I'm not sure, but this is really a statement about acceleration in flat space.
Local. I see. Well, okay. So it's there's something.
I mean, the issue is that when you're, I would say when you're orbiting a planet, I would say you're not accelerating. You're falling on a geodesic. I mean, yeah, this is a bit of, you know, the subtlety of general relativity, but so you're kind of in a locally inertial frame, right? I mean, the people in the space station who are orbiting the Earth don't feel acceleration.
Okay, but there's still,
the people who accelerate, we're the ones who are accelerating, right? Because we're standing on the surface of the Earth.
Yeah. So do we have an undue temperature around here?
Yeah, I think so.
Okay, but in orbit we don't because of
I think that's probably closer to the truth. Yes.
Okay, maybe we can discuss this later.
Yeah, but I haven't thought about it in detail, but that's my expectation for how it works. Okay. So I want to make one other comment before I get back to black holes. So it's instructive to consider what happens if we mess up this entanglement in the ground state. Okay. And so just for illustrative purposes, let's just totally mutilate it. Okay, so let's consider a state where instead of the ground state, we'll consider a new state, which is rho left tensor rho right. So so I take whatever so both of these are thermal, right? So I showed the state on the right is thermal. Of course, the state on the left is going to be thermal too. And then I just take the tensor product of the two thermal states. Okay, I can certainly consider a state like that. So here's an experiment, a thought experiment. Okay, so let's think about what the world looks like in this state, right? Because this is a state where there's no entanglement between the two sides. Okay, and so what we want to think about is what happens. So so if you're living over here, in the right Rindler wedge, nothing happens. You know, the state is the same as it was in the vacuum. Every experiment you do over here, it just gives the same result as it would in the vacuum. Similarly, over here, same story. You know, you can't even tell that you're not in the vacuum, right? You see all the same physics that you would before. But on the other hand, this is a bad state because if you think about this. This gradient term in the Hamiltonian, for example, in free field theory that we were discussing over here, right? You can kind of estimate what that gradient term in the Hamiltonian has to say when, you know, for the gradient term that's sitting right here in the center. And what you find is that it's very unhappy. And in fact, there's an infinite amount of energy sitting right here at the origin of space. And so as soon as you go up into this region, oh boy, there's just a huge disaster, a catastrophe, infinite energy, particles flying everywhere, all the way up to the cutoff, and actually also down in here. So anyone who somehow makes it up into here is unhappy. And similarly, anyone who is somehow down here is very unhappy. And this actually has a name. It's called a firewall. So the lesson is that you really better have that entanglement there if you want, crossing this. So these lines here are sometimes called Rindler horizons. If you want crossing the Rindler horizon to be a pleasant experience, you really better have, almost all of that vacuum entanglement there. Okay, so that's it for sort of quantum field theory in general. Now we're going to go back to black holes, but I'll first ask if there are any more questions.
To get it clear, the picture that you made with the firewall.
Yeah.
We've noted before that as two fields approach one another arbitrarily close, then entanglement increases. And then I understand the picture you draw with the firewall here is that you have, you have the two observers exactly crossing one another at the 0 point, and that's where they feel the firewall, so to say.
Well, yeah, so here there's no entanglement, right? So if you measure like the correlation function of this field and that field, you get 0, okay? But that doesn't matter for someone who's only living here because they can't measure this one. So they don't see that divergent correlation function isn't there anymore until they go across here, and then they see it immediately because there's this infinite energy in the Hamiltonian sitting here. That just kills them. You can try to make it less violent by not having a product state. The product state is like a really extreme mutilation of the state. You could try to just disrupt the entanglement a little bit, and then you would see that there's some blip that they see, and then the blip gets worse as you disrupt more of the entanglement. But since you started with an infinite amount of entanglement, if you disrupt all of it, then you get an infinite amount of badness.
Okay.
Enrico has a question.
Yes, just some curiosity. So we are considering now the Lorentz group, but what would happen if we consider instead the Poincare group?
Not much. I'm
would
sort
we
of
have the same entanglement or thermal states?
In fact, yeah, I'm sort of already probably in some sense assuming that. I mean, certainly when I said that the story is the same anywhere, and if you do the split anywhere in space, I was assuming the Poincare group. Yeah, so to me, relativistic QFT means Poincare. Yeah. All right. So now we're going to go on to black holes, and actually, having gone through the equations for quantum field theory in flat space, I'm going to be much more sketchy talking about black holes, and since the ideas are quite similar, the math is just more complicated. So we'll discuss the ideas, which will hopefully seem plausible given what we just discussed. Let's consider now again. So now on to back to black holes. So let's consider a black hole again that we made by a collapse. We can take it to be a null collapse. Man, I'm really bad at doing this. Wow. Okay. Okay. So the key fact about black holes is that if you want the physics near the horizon, which is this dashed line here, to be well behaved, to not have one of these firewall type things, then at least if you're just doing quantum field theory in the black hole background, in order to have that, the degrees of freedom on either side of the horizon need to be entangled with each other. Because if they're not, then you'll just find yourself in this kind of situation. And so in particular, if you have some degrees of freedom here that are outside the black hole, so these are going off towards null infinity, some modes, This horizon locally is basically the same thing, as basically identical to these Rindler horizons that we were discussing before. And so it has to have an entanglement pattern, which is basically the same as this one. If it has anything else, then there's going to be some kind of disturbance at the horizon. And so in particular, that means that some modes here, which are going out, have to be highly entangled with some modes inside the horizon that are going like that. With some formula that's just like the formula that we wrote before. So then the only novelty, though, is that in the Rindler case, this entanglement, if you were someone who was just kind of drifting along here in this, well, not in this one, that's the bad one, but if you were over here in the good one and you were just kind of drifting along, without accelerating or anything, then you would eventually see both sides. So you wouldn't necessarily think of this entanglement as reflecting genuine uncertainty or genuine thermality. You would just think, oh, those are some vacuum fluctuations. But in the black hole situation, anyone who stays outside the system, so that person will think that these blue modes are in a thermal state for the same reason that we discussed here. But they'll really think that, because anyone who lives out here who ends up, say, at future time-like infinity, is just only ever going to see these blue modes. And so no matter how long they wait or how carefully they measure them, they're really just going to think that they're thermal. And that means that the blue modes actually create an energy flux. Out of the black hole to infinity. And so working out the details of that, so is what is done in Hawking's famous paper, which is called Particle Creation by Black Holes. If you like this subject, you should really look at this paper. From my point of view, this paper is kind of the physics analog of a Beethoven symphony or a Michelangelo sculpture. It's the kind of paper that most of us can only dream about writing. We would be happy if we could write one paper that's a tenth as good as this paper. The key step, which actually isn't that hard, but I'm not going to go through it just because I would have to introduce more equations, is figuring out how to match the time of somebody who just sits outside the black hole far away from it to the time which is generated by this Rindler Hamiltonian near the horizon. Okay, and then once you know how those two Hamiltonians are related, then you know how to convert this Rindler temperature of 2 pi or Unruh temperature of A over 2 pi into the temperature of this energy of the radiation that comes out in this energy flux as seen by the person far away. But it's just a matching of geometries. I mean, we could almost do it using the equations we've written down now. It's just that I'd have to do a few more coordinate transformations and it would just take a little too much time. But you can look in my Jerusalem lectures if you want to see it. But the result, which we already met last time, is that the temperature as seen by the asymptotic observer is just this one we wrote down last time. It's h bar c cubed over 8 pi gm. Okay, so this thermal entanglement across the horizon leads to this energy flux, which is where the state of the blue modes coming out is thermal up to something called gray body factors, which I'm not going to explain, with this temperature, which is the Hawking temperature. So any questions about that? we're going to spend the rest of the lecture just sort of enjoying the consequences of this formula. But this is all I'm going to say about how to derive it, unless you ask me more questions about it.
Can I make a sort of recap? So,
yeah.
So this formula, it was calculated by Hawking on the basis of two fundamental hypotheses that you make a quantum field theory on a space that has a black hole metric, a rigid black hole metric.
Mm-hmm.
Okay.
Yeah. Yeah. Together with the assumption that there's nothing too bad happening at the horizon. That goes into the calculation. Okay. I mean, if you're willing to tolerate this kind of thing, then you don't have to have this formula.
Okay.
But there's an assumption that you make the black hole, whatever matter it collapses in after it's gone, then you didn't throw anything else in, and the horizon should just be smooth. So that's an assumption, which could be wrong. But if it was wrong, that would be pretty crazy. Then you'd have to ask, why is it wrong? Where did all the bad stuff here come from? It doesn't look like there's anything bad. The shell just falls in. Siddharth has a question, or is that old?
No, that's new. I was just can you explain again why you have an energy flux in the case of the black hole horizon, but not in the case of the Rindler horizon? What exactly makes the difference of the flux there?
Yeah, it's really that. The Rindler observer who accelerates does see an energy flux in some sense, right? Like their detector clicks, and it keeps clicking until it equilibrates with the bath of gas that's coming out, right? The difference is that somehow, in order to be that person in Rindler space, you need an infinite amount of rocket fuel, because you just have to keep accelerating and accelerating and accelerating, and that's not very practical. So if you're someone who doesn't have an infinite amount of rocket fuel, then eventually you run out of rocket fuel and you stop accelerating, your detector stops clicking. But for the black hole, you can just be sort of arbitrarily far away from the black hole, right? You can, if you like, you can be orbiting it, very slowly, very far away. So you don't have to work to be the Unruh observer. You just kind of get it for free.
So the Unruh radiation in the case of like Rindler space-time, that radiation can't be sent out to infinity, right? That's sort of the consequence of it.
Yeah, it's not. Someone who is just an inertial observer does not see it.
Right. Won't click. Right. So even if the Unruh observer like opens his window in his rocket ship, and he lets the photon out, right? Someone sitting, an inertial observer won't see that photon, right? Because
well, if they, it depends what you mean, right? Like there are a million thought experiments we can do of ever increasing complexity involving the Unruh effect. Maybe we shouldn't try to go through all of them, but of course you can, as an accelerating observer, you can shine a laser or something, right? And then that'll be seen by the inertial observer. But I think, it's best not to have more than one observer who's communicating, because debugging it'll take too long. But let's just say an observer who is inertial holding a detector, the detector will not click. It's an inertial observer who's watching an accelerating observer will agree that the accelerating observer's detector clicked, but they won't think it comes from vacuum fluctuations. They'll think that it comes from the fact that the detector was accelerating. There's a really nice paper actually by Unruh and Wald that explains how that clicking of the detector looks from the inertial observer's point of view. So it's kind of fun to read that paper. Let's see. There's a question from Jin Zhao, maybe.
Yes. So I was just wondering on the black hole, on the Penrose diagram, can one point out the very event of black hole formation, or and the very event of the first Hawking quanta being emitted? Can one do that?
I think the answer is no. Yeah, that has to do with the physics that I kind of have been suppressing in this lecture, which has to do with the potential barrier between the modes near the horizon and the modes that make it out to infinity. So there's just some fields that are fluctuating, and they, when this, right after the shell goes in, there's some excitement, right? And then stuff kind of gradually rings down, and then you establish this long-term flux. But yeah, I'm not sure. I mean, it's not like the photons come out like, you know, at some definite time in some, you know, very coherent way, right? It's kind of, there's a probability that a photon comes out. You kind of settle down on this probability distribution that, roughly speaking, there's a photon every Schwarzschild time, but, you know, yeah, you don't necessarily, they're not coming out like in a definite state, right? They're coming out in a mixed state.
But is there a point where I can say the black hole has formed?
I mean, with some tolerance, you can say that, right? Like you can say that the quasi-normal modes have rung down to a size which is of order G Newton or something, right? I mean, you could say something like that.
Okay. I'm just curious because sometimes people in the literature say something like certain time scale after the black hole has formed.
But this is not a question. I mean, this is no different than like, I mean, you know, if you have like whatever, like an RLC circuit, right, and you turn it on, and then there, you turn it, you know, it rings down with some exponential decay, and you know, I mean, mathematically, there's no point where the current goes to zero, but you know, I mean, in practice, of course, right, eventually you run into like the fact that current is made out of electrons and it's quantized and so on, right? But I'm not sure if there's a sharp point where you say the current stopped flowing.
Okay. Thanks.
So Kirill has a question.
Yeah, I found this very important to understand what you have drawn on the left-hand side with the experiment where the entropy factorizes into the left-hand part and the right-hand part, and so the two observers don't. I mean, their measurements are not correlated, and then Hawking's calculation which avoids that. And so, could you just repeat what exactly Hawking did in order to avoid this dilemma facing at the horizon?
But he just assumed that, I mean, he assumed that locally these modes are entangled just as they are in this formula, or sorry, in this formula. Okay, that was the assumption. You just, you know, and he had some roundabout way of saying it, but that's what he really said, is he said, this is the state locally near the horizon. It's just like the vacuum. You have exactly this entanglement pattern.
Okay. Yeah, so he assumed that, yeah, okay. Okay.
And if you have that, then everybody's happy.
Mm-hmm. And we don't have the factorization. Okay.
No, the state does not, absolutely doesn't factorize. It's a this very entangled state, this one that we write here.
Yeah.
Okay. So good. So let's spend the last 15 minutes thinking about the consequences of this formula. So one immediate thing is that we can integrate, right? So we can use that dE equals TdS. So last time I ran this logic the other way, but this is the way that the logic actually runs. So we can integrate this formula to tell us that S equals C cubed area over 4G H bar. Okay, so we can immediately get the Bekenstein-Hawking formula once we have a formula for the temperature as a function of the energy. Okay. It's worth emphasizing, though, that this calculation does not give a state counting interpretation of this entropy, right? It's like thermodynamics in the 19th century. You know, it gives us a quantity that obeys the first law of thermodynamics, but it doesn't give a statistical interpretation of that quantity. You know, in string theory, there are some cases, as Sebastian was discussing, where for certain supersymmetric black holes, you can count their microstates, and you find that they agree with this formula whenever you can check it. But that's still only a restricted set of black holes, and you know that's true only in string theory, which may be the only theory of quantum gravity. But you know, anyways, that's not clear for sure. So, you know, the microscopic origin of this, I would say, is still mysterious in general. But anyways, we can at least in the 19th century level understand it by using this formula. Okay, so that's comment number one. So then we can also, so since there's an energy flux, right, that means that the black hole will gradually evaporate. So computing the energy flux is a little bit annoying. It depends on details like what kind of fields are around, what their spins are, how heavy they are, things like that. But roughly speaking, you can get a differential equation that says that the derivative of the mass of the black hole as a function of time, well, equals is too strong. Let's just say scales like minus t squared, which scales like minus 1 over g squared m squared. And so then if you integrate this differential equation, you get that m of t is like the initial mass cubed minus some constant d times t over g squared to the 1/3. Okay, and this is just some order 1 constant that depends on this crud about what kind of fields are around, and you have to solve some numerical differential equation and figure out what the d is. So we're not going to do such grubby things as that here. Okay. And so what we learn is that the evaporation time goes like g squared m cubed. And this is a very long time. So for example, if the mass of the black hole is of order the mass of the sun, then this is something like 10 to the 66 years. So it's a very long time for a big black hole to evaporate. Much longer than the time since the Big Bang as conventionally defined. Although, of course, we don't really know the age of the universe. It could be infinite. Okay, so these are just some basic consequences of Hawking's temperature formula. Any questions about these? Otherwise, we'll make some comments about the information problem. But I'm happy to answer any questions about these first.
It's also very difficult to observe this radiation because it's very small, and in a universe in which the background radiation is so strong like now, it's completely impossible to detect. Yes.
Yeah. So for astrophysical black holes, we're probably not going to directly detect Hawking radiation. That's correct. Yeah. It's the wavelength is very. I mean, the wavelength is of order the size of the black hole, which is about 1 kilometer for a solar mass black hole. So we'd be talking about detecting individual photons whose wavelength is 1 kilometer, you know, in a pretty noisy environment where, like you said, there's the CMB, there's, you know, accretion disks and whatever, and we're very far away. So, you know, probably not going to happen anytime soon. You know, if we could somehow make black holes that are smaller in the lab, then we would be able to detect it. But it's pretty hard to make black holes in the lab. So, yeah. And maybe I'll make a more general comment, which is that, you know, all these puzzles about black holes are not currently in a situation where we're going to be measuring them directly anytime soon. You know, you could choose to worry about that. You could say, okay, well, then why are we thinking about it? You know, my point of view is that this is like Einstein's trains that are moving close to the speed of light, right? I mean, we still don't have trains that are moving close to the speed of light, but if your theory has a place where it gets into trouble, then it's probably worth thinking about, even if you can't directly probe that place, because usually if you can resolve the problem, then you can eventually think of other things that there will be other things that you can measure which you didn't even think about at the time. Certainly that's what happened to Einstein. And there are many other examples like that we could discuss maybe in the break. But I wanted to at least say a little bit about the black hole information problem. So as we discussed, right, I mean, the state of these blue modes is thermal. Okay, it's really thermal, or thermal to a very good approximation. And that's kind of puzzling, because if you think about this process where you make a black hole and then you wait for a long time and it evaporates, then that thermal state doesn't seem to depend on how you made the black hole, right? So as we discussed last time, if you throw a book in or something, it doesn't seem to have the information about what book you threw into it, which seems like it directly contradicts the unitarity of quantum mechanics. So that's Hawking's information problem. So there are three possible resolutions of the information problem, which people have considered. Each of the three has people who like it, although the community has been converging on one of them gradually. So the first option is what are called remnants, which says that the radiation stops when m is of order m Planck, and the information stays in the leftover remnant. Okay, so that's called the remnant option. So then it's okay that there's no information in the radiation, provided that you're willing to accept that this tiny object whose size is of order L Planck, which is 10 to minus 35 meters, is able to store all of the information about how the black hole was made. And in fact, it needs to be able to store an infinite amount of information, because the black hole you started with could have been as big as you want. And it still evaporates down to this fixed size L Planck. And so it has to be able to store an arbitrary amount of information. Okay. And so usually people don't like remnants. I don't like them. I think they're hideous. And one reason why we don't like them is because if remnants are true, then this implies that A is not equal to A, S is not equal to A over 4G, right? Because if they're remnants, then I can just throw, I can have some big black hole where I think the entropy is A over 4G, but then I can just throw a remnant into it. And that remnant can store as much information as you want. So if you want unitarity to be true, then after you throw the remnant in, the black hole has to store that information. That's a lot more information than A over 4G. Infinity is greater than A over 4G. Because the remnant has some finite energy, right? Its mass is m Planck. So it's an infinite amount of entropy and a finite mass, which just sounds awful. Okay, but still there are people who like it. Okay, so that's option number one. Option number two was the one Hawking went for, which is information loss. Okay, where you just say that the evaporation finishes, so there's nothing left, and the state of the radiation is mixed. Okay, and then, but we don't like that one because it says that quantum mechanics is wrong. Okay, but that's another option. There are still relativists who like this option, and I mean, not everyone. I mean, there are certainly still partisans for information loss. And then finally, there's the option which most people like these days, which is unitarity. So for unitarity, we say that Hawking's description of the radiation is coarse-grained, and that actually psi final equals some unitary times psi initial. Okay, so the state in particular, if the initial state of the black hole is pure, then the final state is also pure. And it's related to the initial state by some unitary. So in particular, it remembers how a black hole was made.
Sorry to interrupt you. There's a question by Pavan.
Yeah. No, the remnant is compatible with unitarity because the information just stays in the remnant. That's why some people prefer the remnant option to option number two, to information loss. So I complained about option 1, I complained about option 2, so you might think therefore option 3 is the right one, but actually option 3 is pretty problematic too. And the reason is because if you believe in option 3, then you have to think that Hawking's calculation is wrong, as we discussed last time, right? And why is it wrong? It looks good to me, right? I mean, there's weak curvature at the horizon, there's no reason why when you collapse this shell that it should lead to anything funny at the horizon. And if you think there's nothing funny at the horizon, then you should believe this calculation, at least if you believe in local effective field theory. And if you don't believe in local effective field theory, then you're throwing out one of the you're throwing out another fundamental pillar of physics, right? So then you're saying that that you don't believe in effective field theory. Okay, so whichever option you pick, you're throwing out something nice. There's a question, Rawad.
Yeah, thanks. So option 2 says that quantum mechanics is full. Option 1, is there an option that says GR or thermodynamics is false?
Yeah, I mean, you could try to put option 3 in that, a bit in that category, or option 1. Yeah, I mean, like if, yeah, I don't know. Yeah, I'm not sure. Yeah, somehow it's not clear that solves the problem, I guess. Yeah, or maybe it just seems so revolting that it's not taken seriously. I'm not sure. So I'm sorry, I'm going to have to go maybe just a couple minutes over, if that's okay with the organizers. I guess we started a little bit late, but I'll be done by 35. So the best way to see why this modification of effective field theory has to be large is to study this thing called the page curve. So this is, you study the plot of the von Neumann entropy of the radiation as a function of time. And so what Hawking predicts is that this just increases until you get to the evaporation time. And after that, it just saturates because the black hole is done evaporating. And so there's just some fixed entropy of the radiation afterwards. Okay. So this is Hawking. On the other hand, if you believe in unitarity, then what you have to think is that, okay, maybe it starts increasing like what Hawking said, but then at some point, by the time you get to T evaporation, it has to go back down to 0 because the final state of the radiation should be pure. And so in between, there needs to be some mystery that happens where the curve is going up, but then somehow it turns over and it goes back down to 0. But the slope of this curve is really just a direct consequence of this picture of the radiation, right? That you have this mixed state that's coming out. So in order for this to turn over, it requires one of two things. So it either requires that the outgoing, well, so it certainly requires that the outgoing radiation is entangled with the earlier radiation, right? The only way for this curve to go down is for the modes that are coming out late to be entangled with the modes that already came out. That's the only way to make the radiation less mixed, okay? So you certainly need that. But then to have that, you need one of two things. So then either you need to break the entanglement at the horizon, right? Because if if you look at this picture over here, right? If this blue mode is entangled with some other early mode that came out down here, then it can't be entangled with the red mode anymore, okay? But then that's firewall, okay? And that's bad, okay? So if you break the entanglement at horizon, you have firewall, okay? Or you need to say that the red mode inside is not independent of the early radiation. Right, so the only way that this blue mode could be entangled both with the yellow mode, as it needs to be for the page curve to go down, and the red mode, which it needs to be to not have a firewall, is for the yellow mode, the yellow early radiation, and the red mode to somehow really be the same thing. Okay, for them to not really be independent degrees of freedom. But this implies massive non-locality. Okay, right? Because the distance scale between the early radiation and this red mode inside, it's like, as we discussed, is 10 to the 66 light years. Okay, so we're saying that degrees of freedom that are separated by 10 to the 66 light years are not independent of each other. Okay, and so that's what I mean when I say that unitarity requires a breakdown of effective field theory, right? That's like totally different from what we were just discussing for quantum field theory. It's an insane level of non-locality. Nonetheless, the goal of these lectures is to convince you that this is the right answer. Okay, that this massive non-locality is actually what's going on. And so let me close by just quickly mentioning a couple of reasons why this might not be as crazy, or at least good features of this crazy proposal. Okay, so good features. So good feature number one is that it preserves quantum mechanics and also S equals A over 4G. Okay, so it preserves black hole thermodynamics and quantum mechanics. Okay, so that's good. The other options required us to give up one of those things. Okay, that's good feature number one. Good feature number two is that there is the Hawking radiation. It does have enough coarse-grained entropy for this to work. Okay, so if we estimate the coarse-grained entropy of the Hawking radiation, it's basically a linear gas in one dimension. So the size of the gas is g squared m squared, as we just g squared m cubed, as we just discussed. That's the time of the evaporation. And the temperature of the gas is the Hawking temperature, which is 1 over gm. And this is actually gm squared over g. So that's the Schwarzschild radius squared. So that's like A over 4g. So there is actually enough room in the Hawking radiation to account for all of the initial states of, the full set of microstates of the black hole. And if S were not equal to A over 4G, then there wouldn't be any particular reason why that should be true. Okay, so it's at least feasible or plausible that it could happen. In ADS CFT, we know that quantum mechanics works, and S equals A over 4G works. Okay. And we also know that there exists massive non-locality. So at least in our best theory of quantum gravity so far, we do actually have massive non-locality. We don't necessarily know whether it's enough to resolve the information problem or how it resolves it, but it's there, and so that makes it seem less crazy that might be the resolution. And then finally, and I promise this is the last thing, using modern technology, which we'll learn more about, in some cases we can compute the page curve, and the result is consistent with unitarity. Okay, and so somehow I would say sort of the combination of these various factors has put most people into camp 3, or maybe we could call it like camp 3B. So we're not so camp 3A would be firewall. Okay, camp 3B is camp 3A is like unitarity, but there are firewalls. Camp 3B is unitarity, but there's massive non-locality. Okay, And so my last two lectures are going to be to try to teach you about massive non-locality in ADS-CFT. And with that, I'm done. Sorry for going over.
So thank you a lot for your lecture. So we are out of time, but if somebody has a question, maybe Professor Harlow is happy to answer them. So Siddhartha, please.
Yeah, so I don't mean to keep everybody late, of course, but I guess I missed the step where you argued that massive non-locality implies breakdown of effective field theory. I mean, as such, entanglement, if you just mean entanglement across spatially.
No, but I don't
away,
mean, no,
okay.
I don't mean entanglement. No, because in order for this option 3B to be correct, you need, it's not the state that is entangled between the red and the yellow. It's that they have to actually be the same tensor factor of the Hilbert space.
I see.
Because the only way for the blue thing to be entangled with both of these things is for them to actually be the same.
Right, right.
If you view red, blue, and yellow as all independent, there's no way for blue to be entangled with both red and yellow. And so if you adopt unitarity as your principle, so blue and yellow entangled, then you have to give up the entanglement with red, and then you get, that's the firewall.
Okay, so it's non-locality in the sense that what we ordinarily think is spatially very far away are just the same point somehow.
Yeah, like the Hilbert space does not have the tensor product that we started the discussion of quantum field theory with.
Right, okay. I see. Okay, thanks.
Sure. I apologize for the large amount of material in this lecture, but I just had to get through all of it so that we can get on to the next stuff next time.
So if there are no further questions, that's it for today. And we see each other tomorrow.
One short question.
Yes.
Can you say which of these options a fuzzball falls under?
Well, the fuzzball, okay, so the fuzzball people can't make up their own minds about that question, so I'm not going to try to make up their minds for them. Like if you talk to Samir Mathur, he, on different days of the week, he'll be saying all, he'll probably be on all the different, I mean, I guess he's never on the information loss side. But yeah, I guess I would say he can't make up his mind between 3A and 3B, and I guess I would say that about the fuzzball community in general. Sometimes they sound like they're in camp 3A, and sometimes they sound like they're in camp 3B, but they don't have the equations to tell them what to decide one way or the other.
Okay.
Part of the issue is that they're specialized in extremal black holes, and extremal black holes are very special. In fact, my guess is they probably do have firewalls.
Okay, so if there are no further questions, thank you again, Professor Harlow, for the lecture, and we see each other again tomorrow at 11 Rome time zone. So have a happy rest of the day to all you guys.